Hi folks, because I will be away next week, I've decided to record the lectures and put it on the clue using different segments, each roughly 25 minutes long. Now, let me write down here, this is segment 1, FEA basics. Okay, the computer engineering course that you're taking this summer, about 6 weeks of it is devoted to the finite element simulation. But we are using the particular package CATIA, as a black box. You don't know what's going on inside of it. However, it is important that even though this is a basic course, for you to have some elementary understanding of how the FEA calculation is being conducted in any package. Also, keep in mind that the final exam will have some theoretical questions in it in the form of multiple choice, short true false, short answer questions, and you have to know the material that I'm presenting you in these videos. Let me remind you the discussion that we had in class about what FEA does. Suppose you have a three-dimensional object like that, and it's restrained probably somewhere like that. This is restrained. Things don't move. There may be concentrated forces. There may be pressure loading, etc. Our main interest in FEA or in an engineering problem is to find the displacement of every single point XYZ in the three directions. So, for example, displacement in the x direction, which are denoted by u, displacement in y direction, which are denoted by v, and the displacement in the z direction, which is w. Now, these things, u depends on the point that you take, and incidentally, it also depends on time if you're dealing with a transient problem. And v, the same thing. It depends on x, y, z, and t. And finally, w is x, y, z, and t. So FEA will give us approximation to these values at any time. Our interest may be in the displacement, but there is an underlying reason for doing that. Because once you have the displacements, so the displacements will lead to strains, which can be calculated, and the strains, using material properties that you know, will lead into stresses. Probably stresses are one of the ultimate things that we want as a mechanical engineer. If the stresses are too high, keep in mind about what I said about large stress. You have to be careful about the statement that I'm going to make. If the stresses are too high, the material may fail, and that may not be desirable. The way finite element works is that it takes this three-dimensional object and essentially divides it up into elements and masses, which are interconnected throughout. So these are the masses. This is a mass, lumped mass. Here's another mass. This is a spring, etc. If I wanted to explain to you how this thing works, even for this idealization, it's going to be a lot of work. So what I'm going to do instead, I will make the model simpler so that it is not actually complicated like so. So the particular problem that I'm going to be doing is going to be restraining the displacement in two of the directions. So let us look at the following situation. So we have a spring here, a lumped mass there, spring, another lump mass, spring, another lump mass, and finally the spring attached to the wall on the other side. So these are masses. Okay. Now we have essentially 4 elements here. The elements are of the spring type. So this is going to be element number 1, element number 2, element number 3, and element number 4. And we know that at the end of each element, we have these nodes. So this is going to be node number 1, node number 2, node number 3, and 4, and 5. And let us say that one of these masses is subjected to a force. So for example, I'm going to take a force here, F, which can be a function of time. And obviously these masses are going to move, and the objective is to find the displacement of the masses and the reaction forces of the wall. All right, let's move on with the rest of the numbering and labeling of these things. So let's say that this is stiffness as stiffness K superscript 1, K superscript 2, K3, and K4. And let me also assume that the mass of this piece is M2, this is M3, this is M4. Okay? All right. Now, these masses will move, so this one, for example, moved by the amount x1, which can be a function of time. Now, you might say, wait a minute, that point does not move, and you're absolutely right. So at the end of the day, x1 of time will be 0, x1 of t will be 0 for any time. This one will move by x2 of t, x3 of t, and x4 of t, and finally x5 of t, which is also 0 once all the dust settles. We also have some reaction forces at the wall, reaction forces. So for example, this has a reaction force at node 1, which is unknown, also changing with time, and this one also R5 of t. Our plan is to find the unknown displacement and on the unknown reaction forces. So unknowns are x1 of t, x2 of t, x3, x4, x5, reaction force at the wall, left wall, and reaction force at the right wall. Now keep in mind that this will be 0 and this will be 0. So in total we have 5 things to calculate, 3 displacements and 2 reaction forces. Now in order for me to set up this problem, what I would like to do is to isolate a generic spring element like so. So here is the spring element. We can call it element E with a stiffness of Ke. So on the right side I have a node, on the left side I have a node, but since this is a generic one, why don't I call this thing the left mass and this the right mass? So what have we got here? We have a displacement xr of t, which we have to find, and we have a displacement xl of t that needs to be found. But obviously these displacements are because of some net forces that have been applied. So let's call this thing fr of t, and net, and this one is as fl of t. What I'd like to do is to write the equation of motion for this generic element. Now, to make the argument go smoother, let me assume, although this has no bearing on what we're going to do, assume that the spring is in tension. And what that means is XR is bigger than XL. I drop the argument T here. Now, if that is the case, I can redraw my mass like my spring like that. So spring is in tension. Obviously, there is a force here, and there is a force there, and the magnitude of this force is Ke times XR minus XL. And this spring on the left, the spring on the left side is under a force at Ke times XR minus XL. Now, how about the masses? How about the masses? So the masses, let's draw it here. This is the right mass, and on it acts exactly the same force that you see there, except that it points in the other direction. And we already know that there is a force Fr acting on it, and we already know that it has a displacement xr. And the mass on the left, once again, it has a force acting on it, which is balancing the spring force, which is exactly the same number, but points to the right. And on it, there is Fl, and there is XL. So this is the left mass. Let us write the equation of motion. Let us write the equation of motion for the left mass. So we know that Newton, God bless his soul, says sum of all the forces equal to mass times acceleration. So what is the acceleration? It's mass L, ml, times acceleration of that left mass, so xl double dot, equal to sum of all the forces. And you look at your diagram, you see that you have a Ke xr minus xl plus fl, and that's pretty much it. And when you look at the right mass, you have its mass, mr, times the acceleration of that mass, xr double dot, equal to the spring force is acting to the left, so I will put a minus sign here, Ke xr minus xl, and then fr points to the right. Let me take these two and write it in a more well, organized way. So I'm going to take everything to the left side except for FL and FR. So for this one, we're going to have ML XL double dot plus KE XL minus KE XR equal to FL. And for the second one, we have MR XR double dot plus KEXR minus KEXL equal to FR. This is the equation of motion, but I would like to take one more step and write this thing in a slightly more organized way. Let's see now, how do we move this thing down? Oops. All right. So let me. I'm having a problem here.